Hello. It is now time to do the Chapter 9 review worksheet. This is a nice little summary, nice little review of this stuff of Chapter 9. So let's see if you can do this, and if you want to print out a copy of the worksheet and then try the problem and pause the video and see if you can get things right. I think that would be a good little exercise for you. I'm not saying every single little problem from Chapter 9 is in here, but this is a nice review for you. Once again, if you have any questions about any of this, please let me know and I'll be glad to help you. So context 1 says, Esteban runs several youth football programs in his county. He is interested in the quality of the football helmets he owns. Esteban owns thousands of helmets. If he has statistically significant evidence that more than 20% of the helmets are defective, he will discard all the helmets and buy new ones. So more than 20%, okay? He takes a simple random sample of 180 helmets and finds that 42 of them are defective. Esteban performs a hypothesis test with a significance level of 0.05. Significance level, that means alpha. So alpha is 0.05. So in other words, when we find our p-value, if our p-value is below 0.05, we'll reject the null and have convincing evidence for the alternative. If it's above 0.05, we fail to reject the null and do not have convincing evidence for the alternative. So the first thing you have to do when you do a hypothesis test, and it follows the THAME acronym. So this is the T of the THAME acronym. You have to state the type of inference, and this is a one proportion. So this is a one proportion z-test. So you have to say that, one proportion z-test. Or you have to show the formula for it, which it's easier just to write the name. So then your hypotheses, your null hypothesis is going to be that P is equal to whatever the status quo is. And so the status quo here is in essence 0.220%. More than 20% is going to cause an issue. That's going to cause him to discard the helmets. So the null hypothesis is always P is equal to whatever number's in the problem. The alternative is what you suspect might be true. And so that is going to be that P is greater than 0.2. Okay, greater than 0.2. And so, and then you have to define P. P is equal to the proportion of all of Esteban's helmets that are defective. And there we go. That's how you do the hypotheses. Verify the conditions. All right, so the conditions, I've written them out here. All right, so that is sin. So first of all, it says an SRS was taken, so random condition is met. It has to say SRS or random, one of the two, okay? And so that condition's met. That ensures we don't have bias in our selection method. All right, the next thing, there must be at least 1,800 helmets for our sample size to be less than 10% of our population size. That ensures independence, and that ensures we can use the formula for the standard error. And that's why it said this, he owns thousands of them. Okay, that ensures our population is big enough because we're not using replacement here. When we take out these 180 helmets, we're changing the population, but we're not changing it significantly if it's big enough. Okay, so that's the why behind that. All right, and then the third thing is we have is normality, which is n times p and n times 1 minus p greater than or equal to 10. And we use this p naught right here for our p whenever we're doing a hypothesis test. Both those are bigger than 10, so normality is met. In other words, we have normality in our sampling distribution of all the possible values of p hat. Then it asks us to do this. Find the test statistic p-value, which you do need to know how to do by hand, which I've done on previous videos. We'll just use our calculator here, though. And so we will hit the stat button, and we will go to tests and option 5. One proportion z-test, there's our name. So we hit enter. So our null hypothesis value is 0.2. Okay, our x, that's our number of successes. It's 42. 42 is our number of successes. Don't put a decimal there, please. 108 for our n. And so then our alternative is greater than, like that. Okay, and so then we hit calculate and we got ourselves our test statistic p-value. So our test statistic is, is z is equal to 1.118. Okay, that is our z-test statistic, and our p-value is 0.1318. Okay, 0.1318. So that is how you do that. And so we have our test statistic p-value. Make a decision with the p-value. Now, making a decision with the p-value, we have to compare it to our alpha. If the p-value was less than the alpha, we would reject the null. Since it's greater than alpha, we fail to reject the null. So what we would say there is this. This p-value is greater than 0.05, so I failed to reject the null hypothesis. There is not convincing evidence that, and then you restate the alternative, that the proportion is greater than 0.2. There's not convincing evidence that the proportion is greater than 0.2, but you have to say what the proportion is. Is that the proportion of all Esteban's helmets that are defective are greater than 0.2. So that is, there you go. That's how you do a hypothesis test. That is, in essence, doing the THAME acronym there, and there's your proper conclusion with your p-value. Now, what sort of error, type 1 or 2, could he have done? Now, whenever you're asked about type 1 or type 2 error, I immediately say to myself this: one is hot. One is hot. And what that is saying is type 1 error, the null is true, and it's an error, so I must have rejected it. But I rejected the null. All right, so type 2 error is when the null is false. The null is false, but I failed to reject the null. Okay, so in this situation, we did not reject the null. We failed to reject the null. So we couldn't have committed type 1 error. Type 1 error is when you reject the null, but when it's true. I failed to reject the null. So this could have been type 2 error. If the null was false, this would have been type 2 error. And so that is what, in essence, I said here. Type 2, because we did not reject the null hypothesis. Okay, number 6, interpret the meaning of the p-value. To interpret the meaning of a p-value, in other words, to state it as a probability. P stands for probability, okay? This is different from drawing your conclusion and making a decision with the p-value. Making a decision with the p-value is, comparing it to the alpha and either rejecting or failing to reject the null, or either having convincing evidence or not for the alternative, okay? Interpreting the p-value means stating it as a conditional probability. And that is this: if the null is true, and in fact, 20% of Esteban's helmets are defective, the probability of getting a sample proportion as high as 0.23 repeating, and that's what 42 out of 180 is. So our p hat here is equal to 42 out of 180, and that's 0.23 repeating. So the probability of getting a sample proportion as high as 0.23 repeating or higher in a sample of size 180, just by sampling variability, is 0.13178. So the p-value is the probability of getting a sample value this unusual, assuming the null is true. And if that probability is high, if it's greater than alpha, then we can't reject the null. And if it's low, we do reject the null. But that is what it means to interpret the p-value, to state it as a conditional probability. Okay, so that is that. Now, all right, what values of the sample proportion would cause you to reject the null? Okay, and so remember, our null hypothesis is that p is equal to 0.2, and the alternative is that p is greater than 0.2. And so what we're testing is if our p hat, if our sample value was way above 0.2, we would reject the null. And so here's what our sampling distribution looks like. If the null is true, our p hats are going to be centered, around 0.2, like that. Okay, and they'll vary approximately normally because n times p and n times 1 minus p are greater than or equal to 10. But if our p hat that we get in our sample is way above it, okay, that would cause us to reject the null. Well, how far above do we have to go? And that's what alpha determines. Alpha is the percent of your curve that you're rejecting. So we're given that alpha is 0.05, and so that is telling us to reject 5% of the curve. And the reason we're doing it greater than here on the high end is because this said greater than, okay? And so how do we find this point? The point at which we are going to reject that 0.2 is true and that is inverse norm. So inverse norm with 0.95. And so you remember inverse norm on your calculator. So if you do second vars, which is distribution, inverse norm, and we enter 0.95, which is the area that's to the left of this. See, if 0.05 is above it, it means 0.95 is below it. And I tend to always use the left area. You could do right area here with 0.05, by the way. So our mean is 0.2, and our standard deviation would be the square root of 0.2 times 0.8 divided by 180. That's been our formula for the standard area for about 3 chapters now, the square root of p times 1 minus p over n. We're doing the left area, and so it's that. So anything above 0.249 or so, it would cause us to reject the null, okay? Which the one we got in our sample is 0.23 something, so we wouldn't reject the null. So that is how you do that. Okay, let's look at context 2. So that's pretty much most of the stuff that's in 9.1 and 9.2. So context 2 is from 9.3. It says this: Boris owns an automobile manufacturing company. He wishes to see if there's a difference in the proportion of the company's cars that break down within 2 years and the proportion of the company's trucks that break down after 2 years. Takes an SRS of 200 cars and finds 82 of them break down within 2 years. Takes an SRS of 300 of the trucks and finds 154 of them break down in 2 years. He does a significance test. So in our sample, we got p hat for the cars is equal to 82 out of 200, and that's 41%, 0.41. And then the p hat for our trucks, that is going to be 154 out of 300. And so that is 154 divided by 300. And so that's 0.513 repeating. Okay. And so the question we're asking is there a significant difference? We understand that's different, but is this so different that it's not likely to happen by sampling variability? All right. So it asks us to do a test of significance. So we have 2 samples going on here. We have 2 populations, the cars and the trucks. So the name of our type of inference is a 2 proportion z-test. That's the other big thing in this chapter. The null hypothesis is in essence always going to be that our 2 proportions are equal. The proportion for the cars are equal to the proportion of the trucks. Never put p hats here. We know what the p hats are. We already know the p hats are different. So there's no point in hypothesizing about them. We put the p's here with no hats on them, okay? The alternative is that they're not equal to each other. Nowhere up here does it say we suspect that the trucks have more than the cars. They break down more than, it doesn't say that anywhere. And we can't look at the sample data to try to guess that. So we put not equal to. It's a 2-sided test. The other way of writing this is you could just say the difference is 0. P sub c minus P sub t is equal to 0. And then the alternative would be that P sub c minus P sub t is not equal to 0. Okay, that'd be the other way of doing that. Of course, you define your parameters. P sub c is the portion of all the company's cars that break down within 2 years, and then P sub t is for the trucks. Okay, your conditions, remember when you have a 2 sample thing, they had to be independent random. It says that SRSs were taken, so independent random is condition is met. Okay, then your sample sizes can't be more than 10% of your population sizes, so there's got to be at least 200 cars or 2,000 cars and 3,000 trucks, multiplying our sample sizes by 10. Okay, so that ensures independence. And then now, and so this is a little bit different in section 3. All right, so normality. So the way we check for normality with proportions is n times p and n times 1 minus p had to be greater than 10 for both of our samples. Well, what we're going to do with a 2 proportion is we are going to use a combined p hat, because we're doing the whole hypothesis test assuming the null is true. Well, if we're assuming P sub c is equal to P sub t, we can combine our 2 samples into one to come up with a better estimate, in essence, a larger sample size. And so there's our formula for our combined samples. We add up our total number of successes and add up our sample sizes to get our combined p hat. And so that is that. And so that is what we would use. So that is our combined P sub C. We use that times 200 and use that times 300. And so all those are greater than 10. So that is our combined P hat that we use in our calculations there. Then find our test statistic P value. So this is what we would do. So we would say, you do need to know how to do these by hand, but you can use your calculator certainly. And so we would say stat, we would go test, and so we go 2 proportion z-test number 6. And so for our first sample, it would be 82 out of 200. So we go 82 out of 200. And our next sample is 154 out of 300, like that. Our alternative is not equal to, like that. And so then we go calculate, and there's our test statistic p-value right there. There's our z and there's our p-value. Make sure and write p-value. And so that's how you do that. And so then make a decision. This, and what was our alpha? We were not given an alpha, so we use 0.05, okay? So there's our p-value. So this p-value is below our alpha 0.05. So we reject the null. We have convincing evidence that, and then you restate the alternative. Then you restate the alternative, okay? So we have convincing evidence that they're not equal. So in other words, in this case, yes, there is a statistically significant difference in these two sample values. So, and it does appear that the two population values are not the same. So that is the way you word that. And then the last thing is to make an interval and to make the connection between the interval, the p-value, and the null hypothesis. So let's make an interval for the difference. Let's make an interval. In other words, this p sub c minus p sub t, let's make an interval for it. So p sub c minus p sub t, we want to estimate that difference there. So what we'll do is we will do stat, test, and go down to option B, which is what we did in chapter 8, 2 proportion z interval. Notice it went ahead and automatically entered the values for me, and we want 97% confidence. 0.97 is what it asked for right there. And so we go calculate. And there's our interval, okay? And so we would say, in chapter 8, we would say we're 97% confident the true difference, this thing, is in there. And the connection, though, between the null hypothesis value of 0 and the p-value, so the null hypothesis value 0 is not in this interval. These are both negative numbers. 0 is somewhere over here to the right. And so it's not a plausible value for the true difference. And so therefore it is to be rejected, all right? And the p-value is also telling us to reject, okay, at the level of 97%. So here's our interval, and the connection between this interval, the p-value, and the null hypothesis, this interval does not contain 0. That's the null hypothesis value, and it does not contain it. So it is not a plausible value for the true difference and should be rejected, and I should have made sure and said at the 97% level, because that was the percent of my confidence. That corresponds with an alpha of 0.03. Since 0 is not in the 97% confidence interval, and it's a two-sided test, the p-value be below 0.03. The low p-value below 0.03 also tells us to reject the null hypothesis. And that's it. Thanks for watching the video. If you have any questions about this review worksheet, please let me know.